Conservation laws falsify the multiverse. Conservation laws challenge the multiverse hypothesis. 30 to 50 physical parameters of the universe have been set to values that are very highly specified, within very precise ranges, to enable complex life to exist. This is prima facie proof for fine-tuning of the physical parameters of the universe for life to exist. And, this, then, points to the existence and purposeful actions of a fine-tuner, i.e., God, who created and fine-tuned the universe to enable life to exist in it. To avoid this rational conclusion, some atheists have proposed, or appealed to, the multiverse hypothesis, to avoid the purposeful and intelligent fine-tuning of the universe. However, the multiverse fails to avoid the fine-tuning proof, beyond a reasonable doubt, for God. In this video, we discuss one class of reasons for why the multiverse fails. We discuss other reasons in other videos. Introduction. The multiverse hypothesis, which posits that our universe is just one of many, potentially an infinite number, existing within a vast multiverse, has captured the imagination of both scientists and the public. It offers intriguing explanations for various cosmic mysteries, such as the fine-tuning of physical constants, by suggesting that our universe is just one of many possible configurations. However, despite its appeal, the multiverse hypothesis faces significant challenges, particularly when examined through the lens of fundamental physical principles, such as conservation laws. In this video, we will explore how conservation laws challenge the multiverse hypothesis and why they raise serious questions about its scientific validity. Understanding conservation laws. Conservation laws are foundational principles in physics that state that certain quantities in a closed system remain constant over time. These laws include: 1. Conservation of energy. The total energy in a closed system remains constant. Energy can neither be created nor destroyed, only transformed from one form to another. 2. Conservation of momentum. The total momentum of a closed system remains constant unless acted upon by an external force. 3. Conservation of charge. The total electric charge in a closed system remains constant over time. 4. Conservation of mass energy. Mass and energy are equivalent, as expressed in Einstein's famous equation, E equals mc squared, and are conserved together in a closed system. These laws are not just theoretical constructs. They are supported by extensive experimental evidence and are considered inviolable in our understanding of the physical world. The multiverse hypothesis. The multiverse hypothesis suggests that our universe is part of a vast ensemble of universes, each potentially governed by different physical laws, constants, and initial conditions. This idea has been proposed in various forms, such as the many worlds interpretation of quantum mechanics, the landscape of string theory, and models of eternal inflation. One of the primary motivations for the multiverse hypothesis is to explain the apparent fine-tuning of the physical constants in our universe. The idea is that if there are countless universes, each with different constants and laws, then it is not surprising that at least one of them, ours, happens to have the right conditions for life. The challenge of conservation laws. While the multiverse hypothesis offers an imaginative solution to certain cosmological puzzles, it encounters significant difficulties when considered in the context of conservation laws. 1. Conservation of energy. One of the most significant challenges for the multiverse hypothesis is the conservation of energy. If new universes are continually being created, as suggested by some models of eternal inflation or quantum fluctuations, where does the energy for these new universes come from? In a closed system, energy cannot be created from nothing, it must come from somewhere. If our universe is part of a larger multiverse, the energy that constitutes each new universe must be accounted for. However, the multiverse hypothesis does not provide a clear mechanism for how energy conservation is maintained across the multiverse. If energy is being introduced into each new universe without a corresponding loss elsewhere, this would violate the conservation of energy, one of the most fundamental principles in physics. 2. Conservation of momentum. Similar issues arise with the conservation of momentum. In a closed system, the total momentum must remain constant unless acted upon by an external force. If new universes are being spawned within a multiverse, what happens to the momentum of the p-videos and fields involved? The creation of a new universe would seem to require a change in momentum, but again, the multiverse hypothesis does not provide a mechanism for how momentum conservation is maintained across different universes. 3. Conservation of charge. The conservation of electric charge is another principle that is difficult to reconcile with the multiverse hypothesis. If new universes are continually being created, what happens to the charge balance within these universes? Each universe would need to start with a net charge of 0, or maintain charge neutrality. But how this is enforced across a potentially infinite number of universes is unclear. The multiverse hypothesis does not explain how charge conservation is maintained or how violations are prevented in different universes. The problem of causal disconnection. Another challenge related to conservation laws is the concept of causal disconnection between universes. If each universe in the multiverse is causally disconnected from the others, meaning that no information, matter, or energy can pass between them, it becomes difficult to understand how conservation laws could apply across the multiverse. In classical physics, conservation laws are derived from symmetries in space and time, as explained by Noether's theorem. However, if universes are causally disconnected and operate under different laws and constants, there is no overarching framework to enforce conservation laws across the multiverse. This suggests that each universe might operate independently, without any guarantee that conservation laws apply universally. Implications for the multiverse hypothesis. The conflicts between conservation laws and the multiverse hypothesis raise significant concerns about the hypothesis's scientific validity. If the multiverse cannot account for the conservation of energy, momentum, and charge, it challenges the consistency of the hypothesis with well-established physical principles. 1. The need for a unified framework. One potential way to address these challenges is to propose a unified framework that governs the entire multiverse, ensuring that conservation laws apply universally across all universes. However, such a framework would require a new level of theoretical development and empirical support, neither of which currently exists. Without this framework, the multiverse hypothesis remains speculative and difficult to reconcile with known physics. 2. The limits of scientific inquiry. The challenges posed by conservation laws also highlight the limits of scientific inquiry when it comes to the multiverse. Because the multiverse hypothesis often involves realms beyond empirical observation and measurement, it is difficult to test or falsify using traditional scientific methods. If conservation laws cannot be shown to hold across the multiverse, it may suggest that the hypothesis is more a matter of metaphysics than science. 3. Alternative explanations. Given the difficulties in reconciling the multiverse hypothesis with conservation laws, it may be necessary to consider alternative explanations for the fine-tuning of the universe. Some physicists and philosophers argue that instead of invoking a multiverse, we should seek deeper principles or mechanisms within our own universe that explain the observed fine-tuning without violating conservation laws. Conclusion. 1. While the multiverse hypothesis offers an intriguing way to address certain cosmological puzzles, it faces significant challenges when examined through the lens of conservation laws. The principles of conservation of energy, momentum, and charge are foundational to our understanding of the physical universe, and any theory that conflicts with these principles must be carefully scrutinized. 2. The multiverse hypothesis, as it currently stands, does not provide a clear mechanism for how these conservation laws are maintained across different universes, raising questions about its scientific validity. Until a more robust theoretical framework can be developed, or empirical evidence can be found, the multiverse hypothesis remains speculative, and alternative explanations for the fine-tuning of the universe should be explored. Conservation laws, far from being mere technical details, are critical to the coherence of any cosmological theory, and any hypothesis that challenges them must meet a high standard of evidence and logical consistency. 3. 30 to 50 physical parameters of the universe have been set to values that are very highly specified, within very precise ranges, to enable complex life to exist. This is prima facie proof for fine-tuning of the physical parameters of the universe for life to exist. And, this then, points to the existence and purposeful actions of a fine-tuner, i.e., God, who created and fine-tuned the universe to enable life to exist in it. To avoid this rational conclusion, some atheists have proposed, or appealed to, the multiverse hypothesis, to avoid the purposeful and intelligent fine-tuning of the universe. However, the multiverse fails to avoid the fine-tuning proof, beyond a reasonable doubt, for God. In this video, we discussed one class of reasons for why the multiverse fails. We discuss other reasons for the failure of the multiverse in other videos. Thanks for watching. Please like, share and subscribe, and comment below if you agree or would like to add your thoughts.